Is the screen visible?
Yes, sir.
Yes, sir.
Okay, okay. So we will go ahead. So look at this example. A reservoir, an average area is given. The inflow value, the outflow value, monthly rainfall, seepage loss, reduction in volume, everything is mentioned. So now we have to solve this to obtain the value of evaporation during that particular month. So what I would do is that I will take these values suggested as it is. 1 second. I will take them as it is. See, look here. The month suggested is June 1982. Surface area of the lake is in square kilometer, it is 20. Inflow in cubic meter per second is 10. Outflow in cubic meter per second is 15. Rainfall in centimeter is 10. Seepage loss in centimeter is 1.8. Reduction in storage in the tank, in the lake, is 16 MCM, that is million cubic meter. We have to determine the evaporation happening from the lake during this period, June 1982. So what is the equation meant for the purpose? So here, if you look into, first of all, inflow would add to the storage in the lake. Therefore, inflow is positive. Outflow goes out of the lake. Therefore, it is negative. Inflow minus outflow. Then rainfall, it adds to the collection in the tank. Therefore, plus rainfall. Plus rainfall. Then seepage, which goes into the ground, not part of the storage for the lake. Therefore, you have to deduct minus seepage. Then evaporation, again, out of the storage of the lake, hence it is negative, minus evaporation, hence minus evaporation should be equal to change in storage or reduction in storage. Reduction in storage. Is this equation clear to everyone? With this, it is very easy to solve. Inflow minus outflow plus rainfall minus seepage minus evaporation is equal to reduction in storage. Any doubt with this one? Please respond. Any doubt with this equation?
No, sir.
Okay, okay. Inflow adds to the storage, outflow goes out of the storage, rainfall adds to the storage, seepage goes out of the storage, evaporation goes out of the storage. The net, what it is nothing but reduction in storage. Now, how are we going to calculate this? But you have to do one thing right here. That is, the units of measurement of each of these quantities are different. All of them have to be done in same units. So you cannot change the units. So all units have to be similar. Therefore, let us calculate to begin with everything in MCM, because the change or reduction in storage is given in MCM. Reduction in storage is given in MCM. Therefore, we will calculate inflow in MCM. For example, if you calculate inflow in MCM here, against this I would calculate, it is 10 cubic meter per second. 10 cubic meter per second for the whole month of June. For the month of June, you have 30 days. 30 days. And each day has 24 hours. Each hour has 60 minutes. Each minute has 60 seconds. Therefore, per second, the inflow is 10 cubic meter. Therefore, for the whole month, what it is? So it is 10 cubic meter per second into 60 seconds into 60 minutes into 24 hours into 30 days. So you look here. So 10 cubic meter per second, 60 seconds, 60 minutes, 24 hours per day, 30 days in the month. And to convert this gives the answer in cubic meter. To get in million cubic meter, you divide it by 10 power 6. If you do that, you get 25.92 MCM. Is this point clear to everyone? How to get in MCM inflow? Is it clear? 25.92 MCM. Similarly, you can think of outflow also. Outflow is nothing but 15 star 60 seconds, 60 minutes, 24 hours, 30 days divided by 10 to the power 6 to convert that to MCM. So 38.88. So you get this also in MCM. So you get this in MCM. Then rainfall is given in centimeter depth units. These two are in discharge units. So this is rainfall and seepage are given in depth units. So the kind of calculation to obtain the volume of water in MCM slightly varies now. How do you understand this 10 centimeter? 10 centimeter over the area of the tank. Area of the tank is 20 square kilometers. Therefore, this depth has to be converted into volume by doing this calculation. So here, the depth is 10 centimeter. First convert that to meter, divide by 100. Depth, multiply it with area. Area is 20 square kilometer. 20 square kilometer, but it has to be in meter square. Each kilometer square, that is with kilometer equal to 1000, you have to again multiply it by 1000 square. 1000 square. This gives you the total volume, area into depth, divide by 10 power 6, gives you the value in MCM. This becomes 2 MCM. This becomes 2 MCM. And similarly for seepage also, the depth is 1.8 centimeter. Convert that to meters. Convert that to meter. Multiply this with the area through which it is happening. That is 20 square kilometer. 20 square kilometer. Convert that to meter square into 1000 square. Divide that by 10 power 6 to convert that to MCM. So you get 0.36 MCM. You get 0.36 MCM. Then reduction in storage is 16 MCM. You are already aware. 16 MCM reduction. So therefore, looking into this equation, inflow 25.92. Outflow negative minus 38.88 plus rainfall plus 2 minus seepage minus 0.36 minus evaporation, we don't know, minus evaporation is equal to reduction in storage, is equal to reduction in storage, that is 16. Reduction means negative, that becomes minus 16. So is this equation clear to everyone? Is it clear? Any doubt with this? Somebody please respond.
Yes, sir.
Okay, now I will just simplify this. 25.92 minus 38.88 plus 2 minus 0.36 will be minus 11.32. Therefore, this value is minus 11.32 minus evaporation is equal to minus 16. 1 second. One second. Minus 11.32 minus evaporation is equal to minus 16. So with this, you can easily understand evaporation is nothing but 16 minus 11.32. Evaporation to the right hand side, minus 16 to the left side, 16 minus 11.32 will become evaporation. That is, if you write this, 16 minus 11.32 becomes the evaporation value as so many MCM. So 4.68 MCM. Evaporation is 4.68 MCM, million cubic meter. Have you understood this? Is there any question on this? Okay, somebody has already replied to this, 4.68. Thank you, Suhas. Okay. Suppose if the answer has to be reported in depth units as so many centimeters, how would you calculate using this MCM? Somebody can try and put it in chat box. Instead of MCM, you convert that into depth units, so many centimeters. How would you do that? I wait for a minute. Please try this. In depth units, how would you do that? How to convert 4.68 million cubic meter into centimeter over the area? How to do that? I will show you here. Here, 4.68 MCM is nothing but 4.68 into 10 to the power 6 cubic meter. Divide by the area over which it is the surface area, that is 20 square kilometers, that is 20 star 1000 square. So this gives you the answer in meters. Suppose if you wish to convert this into centimeter, you multiply this with 100, you get 23.4 centimeter. Is this clear? Alternatively, you can express this way also. Is this clear? (23.4 centimeter) is clear. Okay. See, unless you respond, I cannot move ahead. Say either 4.68 MCM or 23.4 centimeter. Either way, the answer is same. At least you type in chat box whether you are following or not. I will get some feedback. Nobody is responding. Yeah. Yes. Okay. 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 Some of them have said. Okay. So then we will move ahead to next example then. So we will go to this example. Another example here. I have done it clearly in centimeter units and MCM units separately. I have done. This I will send separately as a small file. It is not part of the class notes, I believe. I will send it to you. You can make use of this for your preparation. Okay. So 23.4 centimeter, which is very clear here. And similarly, whatever we have calculated, everything is shown here. So you can understand that from this. You can easily. 4.68 MCM, 23.4. The same thing we did. 4.68, 23.4. The same thing. Then, look here. Another example. Calculate the daily operation from class K pan if the amounts of water added to bring the level to the fixed point are as follows. So days in a week are mentioned in numbers 1, 2 up to 7. Rainfall in millimeters is suggested 14, 6, 12, 8, etc. Water added is suggested, but one of the values is shown negative should indicate that it is removal. Any negative value should be assumed as removal. So using this, we have to calculate what is the evaporation loss of water in this particular week from a lake of surface area of 640 hectares in the vicinity, assuming pan coefficient of 0.75. So this is the problem statement. What is the evaporation loss of water in this week from this lake of 640 hectares, which is in the near vicinity, assuming pan coefficient of 0.75. So now just the same table I have taken here, day, rainfall, water added. Of course, minus sign again indicates water removed to keep it at certain level all the time, not to overwhelm the capacity of the pan which is being used for measurement of evaporation. So using this, loss of water due to evaporation is nothing but equal to rainfall plus or minus what we add or remove. If you add, you take plus sign. If you remove, you take minus sign. That is what is done here. 14 minus 5, 9. 6 plus 3, 9. 12 plus 0, 12. 8 plus 0, 8. 0 plus 7, 7. 5 plus 4, 9. 6 plus 3, 9. For all 7 days, you add all these 7 numbers. You add all these 7 numbers. It comes to 63 mm. The total evaporation is 63 mm. So what I have done is that pan coefficient is 0.75, 63 mm converted to meter, dividing by 1000. Then to get the volume, multiply by the area. Area is 640 hectares, and each hectare is 10,000 square meters, 10 power 4. Remember, 10 power 4 is equal to 10 power 4 square meters is equal to 1 hectare. I have multiplied, and that gives you the volume. This gives you the volume in cubic meters. Divide by 10 power 6, you get this in MCM. Therefore, 0.3024 MCM, million cubic meter, is the loss due to evaporation, water loss due to evaporation. So this is another example which you can think of. One more example, probably I have the last one. This is the last one. So here, following are the monthly pan evaporation data at Krishna Sagara Dam in a certain year in centimeter. For all 12 months, evaporation values are suggested. Evaporation values are suggested. The water spread in the lake nearby in the beginning of January is 2.8 kilometers square. And at the end of the year, it is 2.55 kilometers square in the month of December. Calculate the loss of water due to evaporation, assume pan coefficient of 0.7. So the equation is very simple. Pan coefficient into annual evaporation. Annual evaporation is nothing but sum of all the evaporation values for these 12 months. You add all these. If you add all these values, you get the sum. So that sum is taken here. That becomes 228.7. That is in, look here, units of centimeter. So you have to convert that to meter, you divide by 100. This 100 is shown here. 228.7 is the evaporation for the whole year by adding monthly values, divide by 100. Of course, span coefficient is given 0.7, that needs to be multiplied. And then the area of the lake or the water spread is 2.8 in the beginning, 2.55 in the end. Therefore, which area to take? The best approach for us from statistics is take average area, 2.8 plus 2.55 divided by 2. So since this is in kilometer square, convert that to meter square. That I have done by multiplying by 1000 square. Again, I am dividing this cubic meters of water by 10 power 6 to get in MCM. So you get 4.28 MCM. Sometimes what happens is the lake will be in the form of a cone. Hence, by taking the average area like this, which is a simple estimate, may result in erroneous result. So during such cases, a cone formula is also used. Sometimes cone formula is used. If you use that cone formula, this is the equation which you need to adopt. So that also I have shown here. If you use cone formula, this is how you would substitute. So if you substitute this and determine again something similar to this, you get more or less the same value, not much of a difference. The value of the loss due to evaporation is more or less remains the same, 4.28 MCM, not much of a difference. But in few situations, when there is marked difference in the area, if you are assuming the lake in the form of a cone, then in which case using this cone equation will be very helpful. For that reason, you please remember this equation. So that is the only difference. Otherwise, you can take average area also to calculate. So that apart, not much of a difference. Is there any other thing you wish to ask at this stage? Anything else? Please let me know. You can put it on chat box also. If you want to ask anything, I will wait for a while before I move ahead. Anything to ask? Please. I need some response. Otherwise, it is very difficult for me to understand what is happening. Please. Okay. Okay. So then we will move ahead. So you have understood what are the methods which are adopted for determination of evaporation. Of course, you are already aware what is evaporation. And then how to determine evaporation value through numerical examples, we have understood. We have used empirical equations. We have used the concept of pan and pan coefficient to determine evaporation from any water body. And we also understand that it is one of the major abstractions of precipitation. Normally up to 1/3, almost 33% of the water would be lost because of evaporation from any storage water body. So because of which it needs to be controlled so that some extra amount will be available for human needs, plant needs, and such other related needs. So in that perspective, we have to look at how reservoir evaporation can be controlled. A direct determination of evaporation from the reservoir requires accurate knowledge of all items of inflow, outflow, and storage. We have solved one example already. You please remember that. But generally, the method is not so accurate. It is not accurate. In principle, if one measured humidity, temperature, wind at 2 levels above a water surface, it should be possible to compute the upward vapor transport by use of turbulence theory, and many complex equations have been derived to express this relationship. Very complex. Can we think of employing them time and again is another question. One of the simple empirical equation expressed as E equal to this. reservoir. From the reservoir, we are talking reservoir evaporation slightly differently now. We solve numerical examples through some means, empirical equations and pan coefficient. This is another thing. Evaporation E is expressed by this equation too. And this evaporation in inches per day relates to this one. This is a coefficient, okay? And wind velocity at 8 meters above the surface. And these are the pressure values. See here, at 2 levels, we have to measure, which is satisfactory, and we can use this equation also. Of course, we need not consider this as a very strong basis for our examination. Just you remember this equation. So at 2 levels, it needs to be calculated. That is said in this explanation. You can just look at this equation and try to understand. See here, vapor pressure in inches of mercury at the water surface, vapor pressure 8 meters above the surface. So this is what it is. Okay. Then methods to control reservoir evaporation. How are we going to control? So I said this already, 15 to 30% would be lost because of evaporation. First thing is reduction of surface area. So construction of deep reservoirs with very less surface area, because of which the temperature of the sun will not reach so intensely the water body, and hence evaporation can be controlled. Mechanical covers. In some situations, roof covering only for small water bodies, you can think of this. Then chemical films. Use of evaporation inhibitors like cetyl alcohol, hexadecanol, many other things, octadecanol, etc. can be used. But this is dangerous for the flora and fauna. The toxics which are present in such chemicals may impair the living of birds, insects, and the whole lot of diatoms which are present in close proximity to these water bodies, and even may be harmful for the vegetation also. So we have to use them very selectively. It should not be used just like that abundantly and then further getting into the problem. So we are already facing too much of such situations due to exorbitant use of fertilizers, chemicals, insecticides, herbicides. All our water bodies are polluted beyond repair. So we have to be very careful about this. While solving one situation, we should not give invitation for many other problems which are impossible to solve. We may be running out of time in 10 minutes. Till then, we will continue. So this is all we need to discuss in case of evaporation. So the next topic for us is evapotranspiration. The next topic in module 2 for us is evapotranspiration. So in this, we are discussing introduction to evapotranspiration, what we mean by consumptive use, actual evapotranspiration AET, potential evapotranspiration PET, and factors affecting evapotranspiration, then measurement of evapotranspiration, and finally, estimation of evapotranspiration using Blaney-Criddle equation, and numericals would be solved based on this. So what is that we mean by evapotranspiration? So here it consists of two terms, evaporation and transpiration. Evaporation we have already discussed, but here in evapotranspiration, the context is slightly different. Here, the first part, evaporation, which is written as evapo, refers to evaporation which happens from the top soil on which vegetation stands. Of course, the roots will go much below that top soil. That is another thing. When you talk of transpiration, which is the quantity of water consumed exclusively by the plant for its metabolic activities, we cannot separate that distinctly from concurrent evaporation happening from the soil also. So because of which, combinedly, the evaporation which happens from the soil, that is the moisture which is present in the soil, will also evaporate. Along with that, some amount of moisture from the soil is drawn for metabolic activities of the plant. Therefore, the combined term evaporation from the soil, transpiration by the plant by sucking soil moisture, combinedly known as evapotranspiration. So evapotranspiration sometimes is also known by the name consumptive use. That is, the water used by the plant, used by the crop. So evaporation plus transpiration makes evapotranspiration. So that is what I have written here. So you can look at that. So the same thing is explained in many ways here. And then in this, I have also said about the syllabus talks about actual evapotranspiration and potential evapotranspiration. What do we mean by that? Now, you understand water is present in soil in a three-phase system. The three-phase system tells us about hygroscopic water, capillary water, and gravity water or superfluous water. What do we mean by that? Hygroscopic water in the soil cannot be extracted by plants for its needs. That water is present because of affinity between soil and water molecules. Affinity between soil and water molecules. That is known as hygroscopic water. Bottom part of your phase diagram, which perhaps you would have discussed in geotechnical engineering already. Then we talk of what is called as capillary water. Capillary water is the water which is available for plant needs. Plant roots can suck that water in the capillary zone for its metabolic needs. And what is the range within which the capillary water is present? You know what is called as field capacity of the soil. Field capacity of the soil is nothing but total saturation of the soil with water, the moisture, maximum moisture it can hold. That is known as field capacity. Just as we explain field capacity, we also talk what is called as wilting point, the bottommost line below which we have hygroscopic water. The plants can draw water from soil between the range of this wilting level to the field capacity level. And water which is present in this particular zone between field capacity and wilting capacity, wilting level rather, is capillary water, available water to the plant. Anything which is there in the soil above field capacity will stay with the soil for a very brief temporary period, will drain under the action of gravity. Will drain under the action of gravity, and it will go elsewhere, just like how the water flows in a water body. So this is a three-phase system, what we need to understand. For best growth of any plant or crop, the water in the soil, if maintained all the time at field capacity, the evapotranspiration needs are perfectly met. The evapotranspiration needs are perfectly met at field capacity. That means to say that the maximum requirement of evapotranspiration is met at field capacity. If for some reason the soil moisture is not at field capacity, then for transpiration, the maximum requirement is not met. It will be less than that and depends on what is available in that zone between field capacity level and wilting level. Hence, the term here, what we are adopting, actual evapotranspiration, is something which is actually happening. potential evapotranspiration is something which is maximum. Potential evapotranspiration can happen at a level when the water needs of the plant or vegetation are completely met at field capacity moisture content in the soil. For any value less than that, it is the actual evapotranspiration. Hence, we have to understand that actual evapotranspiration values are always less than potential evapotranspiration value. For best growth of the plant, we should make sure that always the plants will get satisfied with potential evapotranspiration. And any reduction from that will result in reduction in crop produce. So this is what we need to understand, the primary thing. So next we will look at what factors affect this evapotranspiration. So I have said it already. See here, there are variety of means by which we can measure them, but there are factors which affect. One second, let me just go back to that. Here, one second. Here, I have written it here. If sufficient moisture is available to completely meet the demand of vegetation covering the entire area, the resulting evapotranspiration is called potential evapotranspiration. The real evapotranspiration occurring under a set of conditions when complete requirements of vegetation is not met is called actual evapotranspiration. For PET, the availability of moisture in the soil should be at field capacity, and for AET is less than field capacity. So this is something what you have to understand, something which would influence this evapotranspiration value. What is present in the soil as a moisture influences that. So there are other kind of things which will influence this evapotranspiration. For example, you take the case of type of soil itself, the type of the crop, the variety of the crop. Each one of them have its own issues in respect of providing water. For example, if you talk of soil, you can have gravelly soil, you can have silt, you can have loam, you can have clay, various types of soils. In each of these types,